Hello guys, welcome to the video on principal component analysis. I am Ritik Bilala. This video is very much important for machine learning engineers and data scientists. You can contact me on ritik.bilala@gmail.com. What is curse of dimensionality? As we all know, when the data increases, the feature vectors increases, we will have the multiple dimensions to deal with, and the complexity or the computation power required will also increase, right? So for example, you have feature vector x1 x2 till x 1000, you will have 1000 dimensions, and in another case you have 5000 dimensions. The complexity to solve or the power required to solve will be higher in the one with 5000 dimensions. So what we want to do is to reduce the dimensions from the data but still want to keep the information with us. So there are various dimensionality reduction techniques for this. PCA is one of them. PCA means the principal component analysis. This gives us the new set of variable which are obtained from the initial set of variables in such a manner that the new set is highly significant and independent of each other, right? So let's say we have two vectors x2 x1 which are mapped to target y. The covariance x1 x2 is definitely not zero. As we can see, x2 is increasing, then x1 is also increasing, right? So can we transform x1 x2 such that the new vectors are independent and still we contain the information with us? Is it possible? So let's see. Now for this, what one thing I can do is to rotate the axis of observation in such a manner that my x2 dash x1 dash new axes are independent. How can we do this? I will explain you with it with the analogy. Just see this, the stress tensor in 2D. It gives fxx, fxy, fyx and fyy. If I apply shear also, then my fyx and fxy terms won't be zero. But suppose if someone asks you to find the direction along which there is no shear, what you will be doing? What we do generally is find the stress tensor matrix and find its eigenvectors and eigenvalue, and then we say the eigenvector is the direction along which the principal force is acting, and there is no shear in that direction. And eigenvalue gives us the principal component, right? We can use the similar mathematics, similar analogy in the principal component analysis. So let's first understand the mathematics. Suppose you have a matrix C in x and y direction, right? So basically, if I want to rotate the matrix C along some x dash y dash, what I can do is multiply p c p transpose, where p is the new orthogonal vectors. So the p is the new directions which are orthogonal, right? Now the important property of the eigenvectors is, if instead of those orthogonal vectors I use the eigenvectors which are also orthogonal, in case of symmetric matrices, the PCP transpose will give me diagonal matrix. It means along the eigenvectors there is principal component, but the convoluted terms like xy, yx, xz terms will become zero because it is diagonal matrix. So this property of eigenvectors and eigenvalues can be very useful in PCA. So first understand this. We have a stress tensor in 3D, and if I perform eigenvector into stress tensor into eigenvector transpose, it will give me a diagonal matrix where E1, E2, E3 are eigenvalues, and these are the principal component along the eigenvectors, and the convoluted terms are zero. X, Y, Y, Z are zero. Now, in case of principal component analysis, we just replace this stress tensor with the covariance matrix. How we can see in next slide. Just find the covariance matrix, right? Now find the eigenvectors and eigenvalues. Now apply the operation PAP transpose, which will give you the diagonal matrix whose elements will be the eigenvalues, and those eigenvalues are actually the variances along those direction, but rest other terms will be zero. The covariances will be zero in the new set of axes. It means the feature have become independent in the particular directions, right? Now one thing is there to uh, which should be taken care of, that the eigenvalues are variances, and variances along directions represent the information particular direction contains. How? So if you have a direction along which there is no variance, so you can say that all entries will be same. So actually this feature vector is not required at all. It is not giving us any information, right? But if any vector has a high variance, it is actually giving us more information, so it is more useful. So you can see the variance in particular direction as the amount of the information it contains. Till now we have just rotated the feature space, right? We have not reduced the dimensions, but after rotating the uh, axis feature space, we when we have found the independent features, space in which the features have become independent, we can reduce the dimensions by dropping some of the features that contains very less information. So for this, what we can do is take the top k feature vectors by arranging the feature vectors according to their descending order of variances, and thus select the first k. K will be upon you, but there is one more method to choose k. What you can do is just plot information contained or the explained variance versus feature vector plot, right? So in this, what I have done on the y-axis, it is the cumulative sum divided by total sum of the variance. So you can see at 400 features, cumulative sum of the features from 0 to 400, cumulative sum of the variances from 0 to 400 features have become 0.9 of the total sum of the features, or total sum of the variances of the 500,000 features, right? So it means that 90% of the information is contained in 400 features. So we can reduce the dimensions from 5000 to these 400, and still we will be having 90% of the information. I will explain you this whole concept by an animation. So understand, first of all, this is a data, and you can see this is not independent. First, standardize the data, then find the covariance matrix C, find the eigenvector and eigenvalues of C, arrange the eigenvalues in descending order, and you know the eigenvalues give the variance in that direction, and the more is the variance, more is the information contained in the direction. Choose the first k directions. And how will you choose k? Summation of k eigenvalues should equal to 0.95 into total summation of the eigenvalues. And 0.95 is a factor which is upon you. Like you can choose 0.9, 0.8 upon your choice. 0.95 totally is actually representing the total amount of percentage of total information you have. Now I found the eigenvector directions and I have put the axis along this. Now I will rotate it. You can see that E2 even are the eigenvectors, and in E2 direction this variance is very low because data is not varying much, but in even direction the data is varying, it is very sparse. So actually most of the information is contained in even direction, so we can actually choose to drop E2. Now I will project the data in even direction, right? Now I have dropped E2, still I have the more than 90% of information, and reduction in reduction of 50% of the dimension is achieved. So thanks for watching. This is my website ritik.bilala@github.io. Please contact me on Facebook.